there, this is Professor Janacek. I want to go over some examples from the skills to prepare us for Calculus 2. The first one is to establish an identity. We have on the left-hand side 1 plus cotangent squared theta. That's being multiplied by sine squared theta, and it should be equal to 1. When establishing an identity, the best thing to do is to start on the side that has the most stuff. Well, in this case, that's definitely this left-hand side. So this is how we're going to start. Remember, you want to work with one side and only one side. Don't try to work on both the left and the right side. We're going to work just on one side and see if we can simplify it down to what we get on the other side. All right. So we always start on just one side, work only on one side, not across the equal sign. The other thing I like to do when I first get started is to rewrite everything in terms of sines and cosines. I'm just used to working with sines and cosines a little bit more than working with some of these other trigonometric functions. So I know that cotangent is, of course, the reciprocal of tangent. Tangent is sine over cosine, so that means cotangent of theta must be equal to cosine of theta over sine of theta. And that's the first thing I'm going to use here on the left-hand side. I have 1 plus cosine theta over sine theta, but since that cotangent is squared, we're going to go ahead and square both of those. All of this is still being multiplied by sine squared theta. Now we'll go ahead and distribute that sine squared. That gives us sine squared theta times 1 is simply sine squared theta. I guess I don't need those parentheses anymore. There we go. Plus, and then we'll take cosine squared theta over sine squared theta, multiply that by the sine squared as well. Okay, well that's not so bad. Next thing I notice is I can reduce those sine squares. So I've got sine squared theta. Oh, by the way, these should be equals all the way down. Notice it's not equals from the first line from my identity. I start after writing my left-hand side, and then I'm going to put equals after that. So now I've got sine squared theta plus the sine squares reduce out of the second term, and we end up with just cosine squared theta. Not so bad. In this, I really like. I recognize this. Just so you know what we did there. This last little bit here is Pythagorean identity. Not to be confused with the Pythagorean theorem. They are related, but they're not the same. Pythagorean identity tells me that this is equal to 1, which is what we were wanting it to equal to on that right-hand side there. Therefore, we have established the identity that 1 plus cotangent squared theta times sine squared theta is equal to 1. All right. That's the first example. On to the second example. We want to simplify 22k minus 44 over 11k minus 44 divided by k squared minus 4 over k squared minus k minus 12. Now this is a rational expression, and we're trying to find the quotient. Remember, quotient means division. So this is a division problem. First thing to do with the division problem when simplifying is rewrite it as a multiplication. So I'm going to go ahead and keep the first expression as is. But now I'm going to multiply by the reciprocal of the second expression. All right, next thing when it comes to multiplying rational expressions, you could simply multiply the numerators and multiply the denominators. But then after that, we would factor. And I think we can just go straight to that factoring step. So the next thing I'm going to do is factor all of this. So let's see, 22k minus 44, I can factor out a 22 and get k minus 2. In the denominator, we have, let's see, factor out an 11, we get k minus 4. Looks good. Now, this second expression, since it's multiplication, I could just put it all together. K squared minus k minus 12. Let's see, that will factor to k minus 4 plus 4. Oh, no. Minus 4 plus 3. There we go. K squared minus 4 in the denominator, that factors to k plus 2, k minus 2. And now it looks like we have lots we can reduce. I can reduce the k minus 2. I can reduce a k minus 4. I can even reduce 22 over 11. So 22 over 11 reduces to 2, and that's going to be in the numerator. We also have a k plus 3 in the numerator, and in the denominator we have a k plus 2. Notice I cannot reduce those 2's because one is part of an addition and one is part of a multiplication. And there we go. That one is simplified. Now we've got one more simplification I want to look at. In this case, we've got radicals, so let's assume that the expressions under the radicals are they represent non-negatives. This has to be told to us. We can't just assume this on our own, but this was part of the problem that was given. So I recognize I have 3 things all under square roots, so we can put all of that together under one big square root. Now, we are still simplifying, so just like the previous problem, I think it's a nice idea to go ahead and factor before we reduce. So I don't have to multiply 55 times 22 and get some large number. I can simply start factoring things. 55 is 5 times 11, and then we have the p. 22 is 2 times 11, and there in the denominator, 10 is 2 times 5, and then we have a p. So notice I didn't actually multiply all those numbers together. I simply factored everything. And now it's going to allow me to reduce nicely. The 5's reduce, the 2's reduce, the p's reduce. Lots of stuff reduces here. So inside this radical, all I have left is 11 times 11. Again, I'm not going to multiply that just yet because I noticed that is 11 squared. And now look at that. I'm taking the square root of 11 squared. The square root of something squared, I just get that something, which is 11. Don't have to worry about negatives here. There are issues with negatives in radicals. This is not one of those cases because I have an even exponent. And there we go. Simplifies down to just 11. Enjoy.